Welcome back to the Drowsy Scientist, where we snooze our way through the universe. We're going on a slow tonight, calming excursion into one of the most pressing issues. Where does space stop? It's a question that sounds simple, maybe even a little silly at first, but the deeper you fall into it, the more it stretches your mind like the universe itself. As always, I hope this video helps you drift off gently, or at least helps you put your worries into perspective by zooming out a few billion light-years. Of course, there's a small risk that it could be too intriguing and keep you up at night. But if that happens, well, at least you'll have learned something fascinating along the way. Before we float off into the stars together, I'd love it if you give the video a like, and if you haven't already, subscribe to it. It truly aids this slumbering little channel expand. Additionally, I'd love to know from where you're watching and what time it is for you right now. Now, are you listening or tuning in at 11:30 p.m. from your warm Stockholm bed, from a couch in Melbourne at 3 o'clock in the afternoon while pretending to work? Please inform me in the comments. It is such a joy to observe the slumbering scientific community dispersed gently around the world. Now sit down. Get used to it. All of this is irrelevant to you. You don't have to pay attention or take notes. Just let the words wash over you, like the background radiation from the cosmos. Remember that this video is, as we begin this gentle journey into the vast unknown, for informational and recreational purposes only. It is not meant to be a substitute for professional medical care or advice. Treatment. Ready? Let's get going. What exactly is space? That silent black canvas that we see when we look at the stars in the sky. What exactly is it? The majority of us, space is nothing at all. A void. A big, empty place where stars float. Socks mysteriously vanish while planets orbit. But space, as it turns out, is nothing but full. In point of fact, it is one of the universe's most active, mysterious, and misunderstood regions. 2. Begin with, let's go back to the basics. People have thought of space as merely a backdrop for centuries. Consider a stage in a cinema. Planets and stars were the flat wooden floor of space, and on top of it, actors moving about. Sir Isaac Newton was largely responsible for this idea, who held the belief that space was a fixed, unchanging environment in which everything took place. Everyone moved through time at the same rate, and space consisted only of a three-dimensional grid. Held all. Then along came a fellow with wild hair and a tendency to scribble on chalkboards, Albert Einstein. He shattered that tidy image and replaced it with something far more strange and elegant. According to Einstein, space isn't a passive backdrop at all. Stretchy and living fabric, one that bends, twists, and warps in the presence of mass and energy. Together, space-time is a four-dimensional construct made up of space and time. Furthermore, this dynamic stage actually reacts to what's going on there. Think of a trampoline to help you picture this. Place a bowling ball in the center and the fabric sags. Roll a marble across the surface at this point. Instead of entering a straight line, it curves around the dip. That's a bit like how gravity works in Einstein's universe. Massive things like stars and planets bend the space-time around them. And that curvature is what we perceive as gravity. We never fall toward Earth because it is magnetizing us. We fall into space as a result of Earth's warped space-time and roll into the dip. Now, you might be thinking, okay, fine, space flexes. But when we're in the spaces between stars, there's nothing in it. Isn't that just nothing? Not exactly. Even in the pitch black, space is still alive, despite being one of the universe's most isolated regions. Thanks to quantum mechanics, we now understand that empty space isn't truly empty at all. On the smallest possible scales, far smaller than atoms, space is buzzing with what physicists call quantum fields. There are no things in these fields. Space. They are the air. It is where all other particles in the universe come from. Corresponding field. A photon comes from the electron field, and an electron comes from the electromagnetic field. These fields are also present even when there are no particles, are never completely still. They fluctuate constantly, producing tiny, momentary particles that appear and vanish like cosmic fireflies. Vacuum energy is the jittery energy in empty space. It's similar to the pond's surface. It appears tranquil from a distance. However, if you get close, you'll see little ripples, disturbances, the occasional jumping fish. What appears despite appearing smooth and featureless from a distance, it actually has hidden motion. This is the reason why physicists assert that there is no vacuum. It sees with potential. Particles pop in and out of existence in fleeting pairs. Virtual particles, as they're known. They can't be directly observed, but their effects can be measured. For instance, they have an effect on the way electrons behave around atomic nuclei and even contribute to the mysterious phenomenon we call dark energy, which is believed to be pushing the universe apart faster and faster. Therefore, contrary to popular belief, space encompasses more than just the location where you misplace your keys or send your thoughts during awkward conversations. Even when it is alive with movement and structure, nothing visible to the eye. When you consider that space itself can expand, it becomes even stranger. Not the items in it moving farther apart, but space itself stretching between them. That idea, too, comes from Einstein's theories, and it underpins our modern understanding of cosmology. But allow us to take a moment to pause. It's easy to feel overwhelmed by the idea that the emptiest thing in existence is actually pulsating with energy, geometry, and invisible fields. However, in a way, that makes it even more reassuring, because it means that the universe isn't just a cold void. Even in its quietest, even in the darkest hours, something is still going on. A soft background hum is like the silence on a still night, the rustle of leaves, or the crackle of a fireplace. And that hum, those fluctuations, that restless vacuum, is a reminder that space isn't just the absence of matter. It is a physical entity with properties of its own. It can expand, bend, and stretch. And the ripple, it has energy. It has temperature. Moreover, even the vast emptiness between galaxies is thought to be just a few degrees above absolute zero, still faintly warmed by the leftover glow of the Big Bang. So, when we ask, what is space? We aren't talking about a void that is empty. We're talking about a complex web that connects each atom and galaxy. Every living being. Things don't happen in space. One of these is space. Things that happens. It's part of the story, not just the stage. And maybe that is by far the oddest thing. Space refuses to be empty the more we study it. It moves, it hums, and it fluctuates, it expands. It is never really doing nothing, even when it appears to be doing nothing. Regarding those missing socks, well, space might not be to blame. However, if they did slip into it, they would, at the very least, be a part of a very exclusive scientific mystery in a pocket of warp spatium. Imagine standing on a tranquil hilltop under a clear night sky, looking up an expansive universe. It feels endless, infinite, eternal. But what if I told you that there's a cosmic limit to what you can see? A kind of celestial bubble that surrounds us. Not because that is where the universe ends, but because light simply hasn't had time to reach us from beyond. This is not a sci-fi story. This is the observable universe, which is the portion of the universe that we are actually able to detect. Gravitational waves, radiation, light, anything that has managed to travel to us since the beginning of time. That word observable is key. It does not imply that nothing else exists outside of it. It just means we're not lucky enough to have seen it yet. Now here's where things get interesting. You might think logically that the farthest we could possibly see would be about 13.8 billion light years away. After all, the universe has existed for that amount of time, plus or minus a few 100 million years. And if light moves at well, the speed of light, wouldn't that be the edge of our vision? If only the universe were that straightforward. Because of the way space itself expands, that boundary is actually much farther out. What we call the observable universe has a current radius of about 46.5 billion light-year in every direction, making it roughly 93 billion light-year across. Yes, that was mentioned, right? Even though the universe is only 13.8 billion years old, the distance too, due to the fact that space has been stretching the whole time. Consider it in this way. Imagine coating a loaf of bread with raisins and baking it in the oven. The raisins get further apart as the bread rises. Now, picture a photon. Just as the baking begins, a beam of light is emitted by one raisin toward another. The bread has grown by the time the light arrives. There was no fixed distance traveled by the photon. It was across a growing one. As the light moved along its path, the destination got further away. That's more or less what happens. On a larger scale, the idea of the cosmic horizon comes to mind as a result of this. It's not a wall. You won't take off on a spaceship out there and suddenly bonk into the edge of the universe like a cosmic cartoon. Rather, it is more like a gentle fading of information. Beyond this horizon, distant regions, light hasn't had enough time to reach us since the Big Bang. We can only see as if we were standing in a vast fog. Nearby glow. The universe shrouds the remainder, not because it is absent, has not yet signaled to us. This horizon forms the boundary of our observable universe, and it's always changing. As time goes on, light from more distant regions will arrive, and the bubble will expand. Simultaneously, as a result of the escalating due to the expansion of space, some galaxies are vanishing so quickly from our horizon that the light they are currently emitting will never reach us, not even in trillions of years. They are vanishing more quickly than light itself, not because they're breaking any cosmic speed limit, but because the space between us is stretching too fast. We are losing control of the universe in a very real way. Let's pause for a moment to appreciate something lovely. Every star, galaxy, and speck of light in the night sky is within our reach. Observable universe. The good news is that. The bad news is almost everywhere. Certainly far more beyond it. Maybe infinitely more that we'll never see, study, or touch. Our instruments are mocked by the vastness that surrounds us. Yet, we are able to only peek through this tiny perception bubble. What's even more humbling is that everyone everywhere has their own observable universe. If you were standing on a distant galaxy 10 billion light-years away, your cosmic bubble would overlap ours a bit, but it would also include regions we'll never know. In other words, the observable universe isn't the universe. It's just our slice of it. And what a slice it is. Roughly 2 trillion galaxies, each containing millions to trillions of stars. This is a lot of starlight crammed into our little observational bubble. The photons from some of these galaxies have been traveling for billions of years before finally being absorbed by your telescope sensor or the back of your retina. Before Earth had even formed, some of that light began its journey tonight. That ancient glow is a kind of time machine, a message in a bottle from an epoch long past. Yet, as affluent as this observable universe is, it may represent only a tiny fraction of the total universe. Beyond the cosmic horizon, space may continue indefinitely. It could be looped, curved, or flat, back on itself in an odd geometry of multiple dimensions. But no one will ever know. With no light, not with any signal bound by time and the speed of causality. That conveys a sense of tranquility. Limit. We are reminded that our place in the cosmos is fundamentally local because we are aware that we cannot see everything. We don't have to comprehend or control the entire universe and discover its meaning. Sometimes it's enough to remind you that you are a part of something much, much bigger than yourself as you sit beneath the stars. And while 93 billion light-year sounds massive, and it's also just the visible frosting on an unfathomably big cosmic cake. What lies beyond? We can only guess. There might be more structure, dark matter, and galaxies. Dark energy and matter. Or maybe something stranger still. But for now, we are currently floating within a glowing bubble of light, data, and time. A bubble that is shaped by photons traveling slowly in the limits of cosmic time, not by borders. It is not prison. It's a present, a slowly expanding gift that lets us see deeper into the story of the universe with every passing day. We can see the night sky when we look up. Frequently, we pretend to be looking at the universe right now, but that's not entirely accurate. What we are actually witnessing is the universe as it used to be. Every glowing dot, galaxy, and star in the sky is a time capsule. The older the light we are seeing, the further away it is. In point of fact, looking out into space is a bit like rummaging through a cosmic attic. Each layer of light takes us deeper into the past. Let's begin with the humble year of light. A light year is the distance that light travels in 1 year, about 6 trillion miles or nearly. 1 trillion kilometers the light you see when you look at a star 100 light years away. Reaching for that star took place 100 years ago. You're seeing it not as it is, but in the same way it was when your great-grandparents were young. Now, stretch that idea across the vast. Since the universe has been around for about 13.8 billion years, time itself has shaped the particle horizon. And the greatest distance at which light could have traveled to reach us today is because of the expansion of space during that time. Around 46 billion light years in any direction. That's why the observable, the size of the universe, is roughly 93 billion light years, is the vast outer edge of everything that we can right now detect. However, do not confuse this horizon with a wall. There's no border, no glowing edge with a no-entry sign. Instead, it's a limit, woven into the very fabric of time. You feel as though you are on the shore of a vast sea. Can look out as far as the light will take you, but you won't be able to see past that gentle curve. Not because nothing exists there, but because the signals haven't had time to arrive. We move on to the universe's event horizon. This is not the same as the dramatic kind that surrounds black holes. Cosmology says the boundary beyond which, regardless of how long we wait, events cannot ever affect us is referred to as the event horizon. It's the cosmic line drawn in the sand. Anything beyond this point flees us more quickly than the speed of light due to the expansion of space. That light, no, will never catch up to us, no matter how patient or persistent we are. It's a little bit like trying to send a message to a friend on a raft traveling downstream in a river. You throw a note-filled bottle, but the strong current overwhelms you. That the bottle cannot reach the raft because it drifts too quickly. No matter how hard you try, the message will never be delivered. That's the event horizon, where communication, even light itself, becomes impractical. The cosmic event horizon is thought to be approximately 16 billion light years away right now. This indicates that there are parts of the universe we can see right now. However, if those regions today emit new light, that light will never make it to us. We're watching galaxies that are in a very real sense slipping away, presently visible, but destined to fade from view forever. Last but not least, the cosmological horizon, which is sometimes used interchangeably with the particle horizon, but can also refer to more general space-time boundaries. It's a term that covers these limits of observation and reminds us that horizons aren't just visual. They have a strong connection to the universe's physics. The cosmological horizon can be thought of as the moving edge of the observable universe, expanding outward as time goes on, and light from more distant objects has the chance to arrive. These perspectives are always changing and developing. The particle horizon narrows as the universe gets older, grows. More light has time to reach us. However, due to dark energy, and the event horizon becomes less relevant as space expands at an increased rate. More galaxies move beyond our reach. The universe becomes an increasingly isolated place, not because it is unoccupied, but because the light from its distant corners is falling behind. In other words, the universe is similar to a balloon slowly expanding. Its surface's dots drift apart, and the further apart they are, the faster they move away. We can only see the dots close enough for their light to make the trip. Beyond that, the light stretches and dims until it vanishes into the expanding abyss. These limits are both peaceful and haunting at the same time. It's a quiet reminder that we can't see everything. Our view is shaped by cosmic history, by how long light has been traveling, and by the peculiar characteristics of the space it traverses. We are looking out of a window that is enormous, yes, but still finite. There will always be some regions of the universe remain a mystery, no matter how patient or clever we become. Not because we lack technology, but rather due to the very nature of space-time. These unseen realms aren't hidden from view behind a curtain. They will never be accessible to information, unknowable. Yet, despite these limitations, we have been able to learn so much. We've mapped galaxies, measured background radiation, and traced the fingerprints of the Big Bang. The particle horizon fog has helped us comprehend the universe's structure and the glow of ancient light to piece together its story. Horizons are not they frame it as limiting our creativity. As the sun rises and burns away the morning mist, every new discovery pushes the fog back just a little, revealing more of the landscape. But there are some will always remain concealed behind the curve, behind the expanding, swollen boundary, and in a place where light will never reach. Still, here we are, spinning quietly in a corner of the universe, watching. Reading the messages they carry, photons arrive from billions of years ago, and dreaming about what lies beyond the next soft bend in the cosmic road. Even if we can't see it all, even if parts of the universe are forever beyond our reach, the beauty is in the trying, in listening to the quiet hum of light, in following it to the edges of knowledge, and in knowing that while we may never see the whole picture, we are still a part of the story. Not too long ago, in the grand timeline of human, people thought the universe was pretty stable out of curiosity. Galaxies were out there, stars were shining, and everything more or less stayed put. A quiet, eternal cosmos. But in the beginning, 20th century, a game-changing discovery quietly rose from a mountaintop observatory, and the universe hasn't sat ever since. Yes, Edwin Hubble, the famous space telescope's name, was the first to notice something peculiar. He noticed that the light from distant galaxies was always redshifted while he was studying them. That entails the galaxies were moving away from us, and the farther away they were, the faster they seemed to recede. It was not a random trend or a cosmic coincidence. It was a pattern, a law. It is space itself, appear to be growing. Now, this isn't quite the same as galaxies zooming through a fixed static. Space like cosmic race cars. It's not like they're expanding into a space that already exists. What's actually happening is stranger and more elegant. Space itself is growing. Imagine that. Galaxies are being carried along with space as it expands, like raisins embedded in a rising loaf of bread. That image, raisin bread, is a gentle and surprisingly accurate way to picture it. Think of the dough as space and the raisins as galaxies. As the dough bakes and rises, it stretches in every direction. Each raisin discovers itself farther from the others, not because it's moving on its own, but because the dough between them is expanding. There's no central raisin, no preferred direction, just a uniformly growing loaf. This is how the universe works on a large scale. Galaxies aren't like cannonballs rushing through space. They're being carried away from each other as the fabric of space itself expands. This is why, regardless of where you are in the universe, everything appears to be the same. Else is departing from you. Space is, from every galaxy's point of view, extending in every direction. It's similar to being inside a rising capsule. No matter which bubble you're in, it seems like all the other bubbles are drifting away. The universe isn't expanding into anything. It's just expanding. It has neither an outer shell nor an edge that it is racing toward. Instead, unbound objects' distances simply increase over time, as if the cosmic measuring tape is gradually getting longer. This concept of expanding, when Hubble first proposed the universe, it was so radical that even Albert Einstein had to revise his own equations. Originally, Einstein had added something called the cosmological constant to his general theory of relativity to make the The universe is still. He thought that the universe had to stay the same and that his equations had to work on their own. Suggested the opposite. Famously, he referred to the addition of the constant as his when he learned of Hubble's findings. Greatest error. Though, ironically, the concept has since made a comeback in explaining dark energy. The universe has an apparent sense of humor as well. Back to the expansion, though. Among the most beautiful outcome of Hubble's discovery was our ability to reset the cosmic clock. Galaxies are, then all of them are now moving on. In the past, they must have been much closer. As a result, scientists came up with the concept of the Big Bang, the hot, dense beginning of the universe. The concept Big Bang has a tendency to lead people astray. It wasn't an explosion in space like fireworks going off in a dark field. It was more like the rapid expansion of space in all directions at once. There's no center, no blast radius, just the universe is suddenly expanding, of an extremely dense and hot state. It is impossible to point to the sky and comment, that's where the Big Bang happened, because it happened everywhere, including right where you're sitting. That expansion is still going on today, nearly 14 billion years later. The light that emanates from galaxies continues to stretch along with their separation. The further something is away the more the expanding universe redshifts its light. It has cosmic, every observation we make is shaped by this stretching of time and space. The expansion of the universe is interesting. Affects not all things equally. It works on the grand scale between galaxies and galaxy clusters, but it doesn't pull your morning coffee farther from your lips or separate the atoms in your seat. This is because on smaller scales, gravity and other forces dominate, ensuring that everything is securely attached. The Milky Way is not getting bigger. There is no doubt that the area is not expanding. And even your laundry will be safe unless your washing machine starts eating socks again. Pile is somewhat stable. However, the expansion continues at the cosmic level. And what's more, it's accelerating. This discovery, made in the late 1990s, came as a surprise. Researchers had assumed that gravity might be slowing down the expansion. Instead, they discovered that some enigmatic force, it is accelerating, now known as dark energy. The dough isn't just rising. With each passing second, it is rising at a faster and faster rate. No one's entirely sure. What is dark energy? It could be a property of space itself, or it could be field that we do not yet comprehend. But whatever it is, it now dominates the energy budget of the universe. That gentle stretch is turning into a cosmic sprint, and galaxies are receding from each other at ever-increasing speeds. In a quiet way, it has a touch of poetry. The universe began with everything close together, dense and unified. Over time, it grew, cooled, created stars, planets, and every component for life. And now it continues to drift outward, aging stars and advancing galaxies apart. Space stretching into the unknown, like a story that opens with a bang, blossoms into complexity, and drifts off into a gentle infinite. Epilogue. Space has no sound, but if it did, maybe it would be the soft dough rising, occasional bubble popping, and warm expansion shifting slowly, not a violent noise, not a shout, just the peaceful hum of a universe becoming itself. Therefore, when we say that the universe is expanding, we are not referring to objects moving away from a point. The very fabric of reality is being stretched as calmly here, and steadily, like baking a loaf of bread. It is not only one of the most significant scientific discoveries, but also one of the most comforting. The notion that change can be steady, gradual, and beautiful. And as we sit here, bathed in ancient light and surrounded by stars, we are a part of that expansion. Every heartbeat, every breath, every single thought you've ever had occurred on a tiny rock that was spinning in the middle of rising cosmic dough. It suffices to make you thirsty for answers, or at the very least, for a snack at midnight. Physics says there's a strict rule that should never be broken. Nothing can move faster than light. Not a spaceship, not a signal, not even your cousin Greg, who claims to have once sped across 6 lanes in record time to avoid traffic. According to Einstein's theory of relativity, the speed of light, the speed limit for everyone is 299 million meters per second, and it can never be reached or exceeded by anything with mass. Yet, somewhere in the astronomers have observed something that appears to defy this rule at great cosmic distance. Luminous galaxies that appear to moving away from us at a rate faster than light. Star clusters in their entirety, and dust moving at superluminal speeds beyond our reach. It sounds like physics should be panicking, but don't worry, everything's fine. The universe is adhering to the rules, simply engaging in an extremely clever game with them. We need to, in order to comprehend what's going on, revisit a major concept. Galaxies are not flying through space like comets in a vacuum. Space itself is instead expanding, carrying galaxies along with it. Space can be thought of as a rubber sheet with dots on it. If you stretch the sheet, the dots move farther apart, not because they're crawling across the surface, but because the surface itself is growing underneath them. This is how galaxies can appear to recede from each other faster than light. They are not going faster than the posted speed limit. It's that the total distance between them is expanding at such a rapid rate, that rate at which light cannot cross. The galaxies themselves continue to follow little physics enthusiasts. Space is carrying out the legwork. A helpful way to visualize it is as follows. Imagine standing on a treadmill. The speed gradually increases. You attempt to approach someone at the opposite end by walking, but the treadmill is moving backward faster than you can walk forward. No matter how hard you try, the distance will eventually between you and the other person keeps increasing. It has nothing to do with you walking too slowly. That's the ground beneath you. You is working against your motion. Light is attempting to move through the expanding universe. Space. But in some regions, especially very far away, space is expanding so rapidly that the light never makes progress toward us. It is comparable to attempting to paddle a canoe upstream in a flash flood. The water flows too fast, and your boat is swept farther away despite your best effort. This doesn't violate, because the theory of relativity only prohibits objects that travel through space faster than light. It says anything about how fast space itself is allowed to grow, and as it turns out, has a lot of talent for making dramatic entrances. Take, for instance, the time period known as cosmic inflation. This was a mind-bendingly brief moment, just after the Big Bang, when the universe expanded at an absolutely staggering rate, which is significantly faster than light speed. The universe was created in less than a trillionth of a second, grew from something smaller than a proton to something the size of a grapefruit, or possibly larger. Make an effort to explain that expansion in a recipe. Again, there were no exceptions to this rapid swelling. It was space doing the expanding, not particles racing through it. It's one of the few times in physics when faster-than-light travel is not only allowed but encouraged. Just don't try it in a spaceship. The suggestion will not be well received by your engines. This rapid inflation smoothed out the early universe, ironing away wrinkles and unevenness like a cosmic steam press. It also contributes to the explanation of a universe's uniform appearance in all directions, despite the fact that distant regions haven't had time to share information because inflation has spread everything out so quickly that differences between became subtle and stretched far apart. Even now, after billions of years, we are still seeing the effects of that expansion. Space continues to expand, bringing far-off galaxies closer together and farther away from us. Now, some of those galaxies are disappearing at a rate faster than light. Not because they are accelerating, but because the distance that separates us is expanding at a rate faster than light can close it. This indicates that there are areas of the universe we can never see. No matter how long we wait, their light will never reach us. Also, if they released new light today, that light would be swept away into the deepening void. Because they're moving too quickly, these galaxies are not lost. Because the road that separates us is expanding at a rate that is faster than their signals can travel. It's a bit like trying to send a postcard across a river where the opposite shore is drifting away faster than you can throw. The postcard is, no matter how many stamps you put on it, never going to make it. At some point, even the concept of delivery loses its significance. Therefore, when astronomers state some galaxies are receding faster than light, what they mean is this. Due to the expansion of space, the separation between us and those galaxies is increasing at a rate faster than light can keep up with. There is no offense, no rebellious physics, just a clever interpretation of how space and time can flex in ways that aren't always clear to our instincts. Actually, this cosmic ruse has an additional bizarre result. There are galaxies we can see today, clear as day, through the most powerful telescopes we have, which have already reached this horizon. Because of the light they emit, they are still visible. Emitted long ago continues to arrive. But their newer light being produced now is already out of reach. Even if we wait forever, it will never reach us. It's similar to looking at a car's tail lights as it turned a corner. You can still see the glow, but the automobile itself has already vanished, cruising down a path you will never take again. The light is a ghost and an outdated message from the past. This reality has a certain peaceful melancholy to it. The universe is full of stories we'll never hear. Stars wheel. Galaxies that we will never discover existed. Not because we didn't look hard enough, but due to the fact that the universe itself is extending the stage beyond our view. Yet this too is part of the wonder. Considering that we've being able to see so much of the past of the universe is nothing short of miraculous. Despite the enormous distance and distortion, we've still managed to see billions of light years in every direction. We have discovered ancient photons. In the middle of the flight, figured out where galaxies came from, and even followed the faint remnants of the original Big Bang. And all of this has happened from a tiny planet orbiting an unremarkable star in an average galaxy in a universe where light travels faster than space. It's enough to make you feel small and strangely fortunate at the same time. We are here because watching light struggle to reach us, counting galaxies, listening to the whispers of an expanding universe as they fade into the distance. Meanwhile, the universe's dough continues to rise, bringing with it the dreams about curious beings who once pondered the limits of light. When we consider the cosmos, it's tempting to imagine it as a large black box. A huge rectangle with a top and bottom, left and right, front and back, just floating in something. Maybe it has edges. Maybe it goes on forever. It's possible that there's a massive cosmic wall marked, "Do not enter," and very security guard who is bored, but the real shape of space is much more subtle and much more intriguing. As it turns out, space is not always flat like a tabletop. It could be curved. In fact, it might be positively or negatively curved or just ever so gently flat. And this isn't just about how it looks. The arrangement of the universe has deep implications for how it evolved, how it behaves, and whether it might one day curve back in on itself or continue stretching forever. Let's start with the three main possibilities. The first is a universe that is flat, like an endless sheet of paper. The geometry rules operate exactly as we learn them in this model. School. Parallel lines never meet. Every triangle always adds 180 degrees. And if you travel in a straight line, you'll never loop around. You'll just keep going indefinitely through an endless cosmic scale. The second option is a closed universe shaped like a sphere, or more precisely, the sphere's equivalent in 3 dimensions. Here, space curves back on itself. If you were to set off in a straight line in any direction and somehow avoided stars, planets, and all, you would eventually return to your starting point from other space debris. Like going around the place in a straight line. Surface of the Earth, you wouldn't fall off. Even if it takes several billion years, you just keep going in circles. Years and a pair of shoes with industrial strength. The third option is still up in the air. Universe shaped like a saddle. This space curves outward like a Pringle. In This geometry, parallel lines eventually diverge. Triangles add up to less than 180 degrees. And if you tried to circumnavigate the universe, you would never return to where you started. Rather, you would simply drift further away and farther out into the cosmic vastness. These shapes, flat, closed, and open, are not merely abstract concepts. They're tied directly to the universe's overall density and energy content. Specifically, how much matter and energy exist compared to what would be needed to make the universe perfectly balanced. At this critical density, space's inward or outward bending is determined. All space is created when the actual density exceeds the critical density, closed and positively curved. If the density is less, it's open and negative curvature, and if the densities match just right, the universe is flat. It's a bit like the Goldilocks of cosmology. Not too much, not too little, but just enough to keep the geometry straight. And how do we measure this? As it turns out, the universe leaves behind clues in the background of cosmic microwaves, the ancient light that has been moving ever since the Big Bang. Scientists can figure out how space bends by looking at the minute fluctuations in this dim glow. Light that travels far. It's like using the pattern of ripples on a pond to comprehend the shore's shape. So far, the evidence suggests something remarkable. Our universe appears to be very, very close to flat. Not perfectly flat, perhaps, but close enough that any curvature is too small to detect with current instruments. It's like being on a huge plane that could have a slight bend somewhere above the horizon, but it's pretty straight as far as you can see. Now, here's where things get incredibly intriguing. Even if a universe is flat, it can still be infinite. And as sealed, surprisingly, the universe can be infinitely large. That phrase sounds like at first, it's a contradiction, like saying you have a full mug but no coffee in it. But it makes sense with a little thought. Take the surface of a sphere. It's finite. You can measure the total area, but it has no edges. You can walk around the surface of a globe forever and never fall off the edge because there is no boundary. The whole surface connects back on itself. Take that now, concept, and apply it to a three-dimensional version. According to cosmologists, a space that's finite but unbounded. It's a self-contained bubble of a closed-loop geometry. There is no border in this type of space. There's no place where the universe ends and something else begins. It's just space curving back around in a grand subtle loop. And we would never be able to tell for sure because we live within it. We just keep drifting forward thinking we're going straight, silently bending in the direction of home. Even in a flat or open universe, infinity has its own distinctive flavor. A universe without end is an endless number of galaxies, stars, and potentially even repeating patterns. Somewhere out there, if the universe is truly infinite, there could be another version of you listening to this same video, possibly in a slightly different pair of pajamas. Now, it's worth noting that we can only observe a small fraction of the universe beyond our observable horizon. We aren't know how space behaves. It could remain flat for all time, or it could curl into a loop that we cannot see because we are so small. The curvature may be so minute that it cannot be seen by a light beam traveling billions of years. It's like attempting to tell whether the Earth is round while standing in a meadow. You don't see the curve, but it's there all the same. Cosmic geometry also affects the fate of a universe. In a closed universe, gravity might eventually slow down the expansion and cause everything to contract, leading to a big crunch. In an open or flat universe, expansion could continue indefinitely, thinning out matter and cooling the cosmos into a gradual fading, though, with dark energy pushing things apart ever faster. With what we know now, a big crunch seems unlikely. What is particularly reassuring about a quiet kind of way is that no matter the shape, we're part of it. We are woven into the structure of the universe, which loops, drifts, curves, and stretches. Its geometry dictates to our atoms. Its curves are traced by our light. Its corridors echo with our thoughts. We do not merely reside in space. In a mass dance, we are space folded into itself. And movement. Therefore, if the universe is flat, we reside on a vast cosmic plane. Possibility. If it's curved like a sphere, we may be looping around inside an invisible bubble. We're there, if it's open, navigating an interminable saddle and venturing out into infinity without a planned return trip. Whichever version is true, it's strange, sophisticated, and exquisitely perplexing at the same time. And that is a component of the magic. You don't need to pin down the shape of space to appreciate its mystery. You just need to you're standing on a small piece of something grand and curious as you look up at the stars and smile. The universe with an internal shape that we are still trying to imagine. Imagine you're a tiny creature living on the surface of a balloon. You can walk north, south, east, and west along the surface, but you can't go below it or float on top of it. Your entire world is that. Skin with 2 dimensions, curved but seamless. You're unaware that the balloon is held by a giant cosmic toddler with a helium tank. You are aware that if you walk straight, you will eventually return in a loop to where you began. This is the magic of curved space. It plays by rules that do not always correspond to our typical experience. However, once you get into its rhythm, it makes perfect sense. And, despite the fact that humans inhabit 3 dimensions of space, 2-dimensional curved surfaces provide us with a surprisingly useful way to imagine, on a much larger scale, what our universe might be doing. Let's, on a flat surface like a sheet of paper or a calm tabletop, begin with something straightforward. The familiar behavior of geometry ways. The angles of a triangle can always add up to 180 degrees. When 2 parallel lines are drawn, they will never cross. And you'll keep going if you start walking in a straight line. Forever, unless you happen to spill coffee or hit a wall. However, now picture yourself walking on the surface of a sphere, such as a planet or the balloon we discussed earlier. Acting somewhat oddly, if you use great circles to draw a triangle, like the equator and lines of longitude, the angles can add up to more than 180 degrees. Parallel lines rarely remain parallel for very long. At the poles, they meet or drift apart based on the direction. Most importantly, walking in a straight line over this curved surface will result in eventually return without ever turning around to where you started. There are no borders, no edges, just a continuous loop. From your limited perspective on the surface, the space around you feels infinite. However, in reality, it is limited and curved back on itself. Now, take that idea and make it bigger. Consider our entire universe as a 3-dimensional version of that balloon surface. Except, instead of curving in 2 dimensions, it's curving in 3, or rather in A. Because it curves in higher dimensional space, it is hard to visualize. I and you both reside within this 3-dimensional, similar to how the balloon creature moves through space without ever seeing the outside, close to the balloon. The galaxies are like the dots on the balloon's surface in this analogy. The balloon expands, and the dots get further apart. Not because they're crawling across the surface, but because the surface itself is stretching. This is what cosmologists mean when they say the universe is expanding. It's not that galaxies are traversing space like comets on vacation. It's that space itself is growing, carrying galaxies with it. And just like our little balloon creature, if the universe is truly curved and finite, then traveling in a straight. If you stand in line for long enough, you might end up right back where you started. Space would not swallow you whole. Due to the lack of an edge, the loop ends without a hitch. It's a finite space with no boundary, which is a strange and lovely idea. You could travel through a finite universe in an infinite amount of time without ever crashing into a wall, but never running out of space. Additionally, the balloon analogy aids us. Comprehend something additional. Why there's no special center of the universe. Just as there's no single center on the surface of a balloon, the universe doesn't have a central point from which everything is expanding. The expansion happens everywhere at once. All points during inflation, the balloon moves away from each other. You could pick any spot and call it here, and the view would appear identical in every direction. It's worth pausing here to note that the balloon analogy isn't perfect. It is merely a model to assist our three-dimensional brains in comprehending a concept of a higher dimension. The balloon's surface is two-dimensional and embedded in three-dimensional space, which we can see and picture. However, if our universe, it could be curved in a higher dimensional space that we are unable to directly observe. It's not floating in a larger container. Space doesn't need an outside to curve. It can naturally curve by its own properties without any external references. One is the concept of intrinsic curvature, of the great insights of Einstein's theory of general relativity. Space and spacetime more broadly is an A. As a background, it has structure and a shape that can change over time. Mass and energy indicate how to curve, and the curvature of spacetime tells matter how to move. It's a relationship that is beautifully circular and controls everything, from the behavior of galaxies to the orbits of planets. On more extensive scales, the curvature of space also affects the path of light. Light does not travel in straight lines as we know them in curved space. It follows the shortest path available, known as a geodesic, that is a large circle on a sphere. It has a curved path in our universe that bends under the influence of gravity and the shape of space itself. That's why massive objects like stars. Gravitational lensing is a phenomenon that occurs when black holes bend light. So when we gaze out at we are not just seeing objects scattered across a flat, empty space in the night sky. We can see a moving light web through curved space, stretched and bent and shaped by the mass of everything within it. It's like looking at the stars through a slow-moving funhouse mirror, except the distortions tell us something true about the shape of the cosmos. Now, let's return to our balloon one last time. The distances between the galaxies on its surface increase as it expands. But the galaxies themselves don't expand. They don't change in size. This is due to the fact that the expansion of space occurs on a large scale between objects and not gravitationally bound together. Therefore, our galaxy, our solar system, and even none of the planet's crusty old coffee shops are being stretched like taffy. The growth only takes root in the great emptiness between galaxies. And what's driving this expansion? Well, we now think that the universe is expanding because of dark energy, a mysterious form of energy that is already present in space. Accelerate its expansion. It appears as though the balloon is doing more than just inflating. So faster and faster with every breath. We are unsure precisely what dark energy is, but its effects can be observed in the motion of far-off galaxies and in the way ancient light stretches across the sky. So, where does this leave us? It means we live in a space that might be curved, that might be finite yet boundless, expanding yet centerless, shaped by rules that defy our everyday experience, yet make perfect sense within the vast dance of the cosmos. Additionally, the potential, the expansion, and the curves of returning to our starting point in a loop can be imagined using a straightforward balloon, a floating through thought space like a rubbery metaphor, whispering ancient secrets about a universe that never grows outward from something, but within itself. Next time you see a balloon rising into the sky, give it a little nod. Even though it's filled with helium and squeaky fun, it also has the shape of something much larger, greater, a gentle curve, a stretch of space, and the quiet idea that maybe the place you started is also where you're going. Just now to get there, you've traversed the cosmos. Infinity. The word itself feels as though it ought to echo when you say it. It's huge, enigmatic, and more than a little scary. It conjures up images of infinite space, stars, and mathematical concepts, problems that make high school students reconsider their life choices. However, what exactly does it imply when we ask, is the universe infinite? Is space truly endless, with no end in sight? A final border or wall? Or is there something more subtle going on? Let's begin with what we already know. Everything we've measured so far about the universe's large-scale structure suggests that it might be infinite. Cosmic microwave observation space is extremely vast, as evidenced by the faint afterglow of the Big Bang in the background. Close to being flat, but not as flat as a sphere or as curved as a saddle. Flat in a geometrical sense. Furthermore, in the framework of general relativity, a flat universe could very well be infinite. If it isn't, it is at least significantly larger than the portion we can observe. That leads us to the observable universe, the cosmic bubble we can see. It stretches about 93 billion light-year across. That's the part of the universe. Because light from those regions has been able to reach us since the beginning of time, we have access to it. But beyond that, it might continue. There might be galaxies upon galaxies, cosmic, structures that we will never find, and entire areas of space that will never be visible to us. And here's the thing, we can't actually prove or disprove whether the universe is infinite because we are confined to our observational limits. We're like ants on a beach looking in every direction and seeing only sand. For all we know, the beach stretches across the continent. Or perhaps it reaches its conclusion in a tide pool filled with curious crabs. We simply do not have enough vision to know. An important point is brought up here. We aren't. Measure infinity the way we measure, say, the distance to the moon. You can't. Place a ruler on the space and proceed until the numbers are exhausted. Infinity is not an integer. It's an idea, a concept, and in science, concepts need evidence. Here's where things get tricky. You can never directly observe infinity. Space can only be used to look for evidence that says signs of curving back on itself, or ending abruptly, or behaving in a way that implies it loops. We have thus far looked everywhere and couldn't find a sharp edge, a sudden drop, or cosmic fence with a sign that says do not pass on it. But that doesn't mean such a thing doesn't exist. It just means that it is beyond our vision. And unless we come up with a telescope suddenly that can break the speed of light and outrun the expansion of the universe, that's not going to change anytime soon. The idea of an infinite universe brings with it some very peculiar consequences. If space is truly infinite, then the amount of matter it contains is also likely infinite, or at least so staggeringly large that it might as well be. That indicates an infinite number of stars, planets, comets, dust clouds, and indeed, the possibility of life. Somewhere in the most distant reaches of a universe that never ends, there may be another planet similar to Earth. It might have oceans that sparkle in strange colors, or trees that grow sideways. It's possible that creatures there are asking the same questions as us, and whether there never ends the universe. And this is where it begins to slightly sway the mind. In an infinite universe, if matter is distributed more or less uniformly, then the laws of probability suggest that patterns will eventually repeat. This indicates that there might be one or more versions of you somewhere out there. Some might be almost identical. Others might have chosen a different breakfast cereal this morning and accidentally altered the course of their entire day. Now, don't worry. This is not meant to cause any anxiety. You won't bump into anyone at the grocery store, into your cosmic doppelganger. These regions are likely so far away that they are forever unreachable. Even if we try, the light from those parts of space will never reach us. If we wait longer than the age of the universe, multiplied by every grain of sand on Earth, still the implications are profound. Size is just one aspect of infinity. It's a change in thinking. It transforms the universe into something infinitely vast. You need not wonder any longer what lies beyond the map's edge, because there is no edge, but rather more map forever. Of course, there are good scientific reasons to be cautious about assuming the universe is infinite. We only have a small sample from which to work, and cosmologists remain open to the idea, despite its size, that space is still limited. It could curve gently back on itself in a way we can't yet detect, circling in new directions or taking on a shape that's unlike anything we've ever seen before. There's also the question of time. The universe might be infinite in space, but finite in duration. It started out this way, what we refer to as the Big Bang. And while the notion of a beginning is itself slippery, it suggests that even if the The universe is infinite and has not always existed in its current state. Philosophically, infinity challenges the way we relate to the universe. Most of the things we do every day have limits. The number of cookies in the jar, our energy, and our time. Infinity breaks that mold. It removes the boundaries and opens up a playground of endless possibility that can be both motivating and overwhelming at the same time. A few ancient the concept of infinity deeply disturbed thinkers. Aristotle, for example, believed the universe must be finite due to the fact that actual infinities were simply too bizarre to accept. And even today, some scientists and philosophers debate whether true infinities can exist in the real world or whether they're merely helpful abstractions. However, contemplating the universe has value regardless of its infiniteness. It stretches the mind, invites humility, and reminds us how small our perspective really is. When you look up at the stars, you're looking into a mystery so vast that even the most daring measurements can't fully capture it. Barely scratch the surface. The cosmic mansion's window only has a few lights and a local glow. And yet, here we are, tiny creatures on a spinning planet, wondering how far space goes. We make instruments to look for ancient light. We come up with math to frame the unthinkable. And we lie awake at night thinking about what lies beyond the last star we can see. Maybe the universe is infinite. Maybe it's not. Either way, it's more than enough. More than enough to fuel our inquiries, tales, science, and aspirations. Sufficient to remind us that we are a part of something truly enormous. The best part of all is that you don't have to know how far it goes to feel at home in it. It already has you woven into its fabric. A flicker of thought on the edge of the observable, glowing softly in a cosmos that may never end. There's something alluring about the idea of having an edge. We are raised with boundaries, walls, fences, sidewalks, lunchboxes. Everything we encounter seems to stop somewhere. Therefore, when we consider the universe, it stands to reason that it too must come to an end. Surely, after some, space must come to an end at a truly staggering distance, such as the last room in a huge mansion or the edge of a huge tabletop that dangles over the abyss. But here's the twist. Space is not actually need an edge. It does not have to have any boundaries at all to be limited in size. And that's where the tension builds. Beautifully strange. Let's start with something simple. Picture the surface of the Earth. If you were to walk in a straight line in any direction, you would eventually circle back to where you started. You wouldn't tumble anything. You would not encounter a wall, and you wouldn't find a signpost reading end of Earth. Please turn around. The surface is finite but unbounded. It loops back around itself without any problems. Now take that idea and expand it to a space with 3 dimensions. Imagine living inside a volume of space that encloses itself in a manner similar to the globe's surface has 2 dimensions. If you could continue moving in a straight line, you may eventually return to your starting point through this space, having never encountered a wall, cliff, or any kind of edge. Space like this doesn't exist in science fiction. It is an excellent model in cosmology. It's called a finite, unbounded space. At first, it sounds like a paradox, like saying that a cup can be full of tea but not contain any liquid. But once you understand the geometry, it clicks into place. Space can be shaped to close in on itself, forming an entire volume without ever having to end. 1. The torus is one of the traditional shapes used to illustrate this concept. Imagine a donut, not the jelly-filled variety, but smooth, round kind with a hole in the middle. The surface of the donut is 2-dimensional. It's walkable around, without leaving the surface, but it has no edges. It loops back around on itself, and vertically and horizontally. You can go if you're an ant walking on the donut, forever without ever hitting a boundary. Now imagine a 3-dimensional version of that where space loops in multiple directions. Although this does not imply that the universe is shaped like a pastry, it does assist us in imagining how space might behave if it were finite and without a border. You could begin with 1 point in space, travel in a straight line, and after a very, very long time, like a cosmic boomerang, you'll find yourself right back where you started. Video provides yet another useful analogy. Games. In certain classic arcade games like Pac-Man or Asteroids, if you move, your character disappears from one side of the screen and reappears on the other. It's not that there's an invisible tunnel on a map that wraps around itself. They just completed a loop. These are two-dimensional versions of a space that is too idle. The size of the game world is limited, but the edges don't act like walls in the real world. They get along. In theoretical cosmology, this idea is more than just playful musing. Some models propose that the universe could have a topology, its fundamental shape that returns in subtle ways in a loop. These loops may go unnoticed unless we looked in the right direction and sufficiently far away. Even the possibility that the universe is small and curved just right, we might see repeated patterns in the cosmic microwave background, like mirrored wallpaper left. Following the Big Bang, we haven't seen any obvious evidence of this repetition yet, but the concept hasn't been ruled out entirely. The universe does not require an outer surface or a surrounding void, according to the deeper truth. That's a very human way to look at space. There's something sitting inside something else. However, space is nothing, embedded in a bigger thing. Is the thing. It's not like a balloon floating in the air. It's more like the entire balloon itself, with all of us stuck on its surface, unable to step outside and look in. Even if the universe is infinite, it still doesn't require an edge. Infinity isn't a place. It's a property. Saying the universe is infinite is like saying numbers never stop. To determine that one does not exist, you do not need to locate the final number. In the same way, you don't have to find the edge of space to know that it might not exist. Edges also create philosophical headaches. What lies beyond an edge, if there's one? More space? Something completely different? A blank nothingness that sits awkwardly waiting to be defined? The moment you introduce an edge, you introduce a paradox. If there's something beyond, then space hasn't genuinely ended. And how can it even be said to exist if there is nothing at all? By contrast, a universe without edges completely avoids this confusion. It simply is. You might come full circle or keep moving forever. There's no edge to fall off, no cosmic warning signs, and no need to define what's beyond the beyond. This does not mean that we will always inquire about boundaries. We are programmed to think in terms of containers in our minds. We like middles, beginnings, and ends. But the universe doesn't seem to care much for our mental filing cabinets. It stretches, curves, and possibly loops, all without offering a clean border to sign off on. Interestingly, even if time might have edges, but space does not. At least from the beginning, our universe, our perspective, with the Big Bang around 13.8 billion years ago, that is not a moment in time, but rather a moment in space itself, started expanding from a previous state. The question of what preceded the Big Bang is like asking what's north of the North Pole. The question is not meaningless, of course. That's how we usually coordinates cease to function. All of this paints a picture of a universe that is a lot more mysterious and subtle than a giant box. It's not an object you can lift the lid on or peek around the side of. It's more like a melody that plays itself, forward, wrapping around dimensions, and humming through time with no final note. There is no chord that ends, just an endless variation. And there are no hard notes in that melody. Connections, curves, and continuations are the only edges. Whether it stretches or loops, the universe does not close off indefinitely like a room. It opens up like an idea, not bounded by walls, but shaped by relationships, light, motion, time, and gravity. Thus, so if you've ever imagined a spaceship sailing bravely toward the edge of the universe, picture this instead. A lengthy, peaceful journey that never comes across a cliff. Only more stars, questions, and space. Not because the universe cannot possibly end, but because it never had an edge in the first place. Before there were stars, before there were galaxies, even before atoms had properly settled into their roles, there was a glow, a soft, Uniform light, like a warm fog, covered the entire universe. Direction. It wasn't a firework display, a spotlight, or a flashbulb. It was quieter and more gentle than that, similar to the first rays of dawn breaking through a window before anyone's had a chance to open their eyes. And some of that light is still with us today. We refer to it as CMBB, or cosmic microwave background, is its abbreviation. It's not just the oldest light we can view, it is the oldest visible light. A whisper from the very early universe, still gently moving through galaxies and stars as it moves through space, planets, and sometimes with the right instruments into our detectors. To understand where this light comes from, let's go back in time, way back. About 13.88 billion years ago, the universe began in a hot, dense state. A singularity of sting energy and unfathomable temperature. From the very beginning, space expanded quickly, dispersing the energy like batter in a pan. The universe expanded, it cooled slowly, not quickly, like a cosmic kettle being slowly removed. The stove. At first, the universe was a blinding soup of particles and radiation. The particles of photons light bounced around constantly, trapped in a fog of charged particles. Electrons and protons whizzed around separately, and light couldn't get very far before being scattered in a new direction. Imagine trying to see through a dense cloud with a flashlight. That's what the universe was like for its first few hundred years. Opaque, chaotic, and full of restless motion. But then something magical happened. About 380,000 years after the Big Bang, the universe cooled enough for protons and electrons to combine into neutral hydrogen atoms. Recombination is the poetic name for this point, and it influenced everything. Light was produced because there were fewer charged particles to disperse. Suddenly, I was able to travel. The fog lifted. The universe became transparent, and the first light came on. That ancient light that spread throughout the universe has since then traveled extensively. It spreads out and covers the entire universe, out by billions of years of cosmic expansion. Once a searing blast of ultraviolet energy has now been reduced to a whisper rather than a loud microwave hum. Roar. However, it is still present all around us, including in your room right now. Moment like a soft, invisible breeze from the beginning of time. The CMB came to our attention almost by accident at first. Robert Wilson and Arno Penzias were two radio astronomers who worked in the 1960s. Were examining radio signals with an enormous horn-shaped antenna. They kept detecting a persistent background noise. Where they pointed their antenna, they cleaned the equipment, double-checked their math, and even removed some pigeons nesting in the device just in case it was their fault. But the sound remained uniform, steady, and oddly cosmic. What they had stumbled upon. The glow that lingered after the Big Bang, without anyone noticing at first. It was predicted to be the cosmic microwave background, by theory, and now detected in all its subtle glory. That faint hiss on there. Radio signal turned out to be a window into the infant universe. Since then, the CMB has been mapped by scientists in amazing level of detail. Space missions such as the Planck, WMAP, and COVE, this ancient light, has been captured in high resolution by satellite. What else? They revealed is more than just a glow. It's a cosmic blueprint, a snapshot of the universe when it was just under 500,000 years old. At first glance, the CMBB looks incredibly uniform. The same brightness and temperature regardless of perspective. However, if you zoom in, you'll see minuscule variations just a few millionths of a degree apart. There are little warm and cold spots. These supple ripples aren't imperfections. They're the seeds of everything. Tiny densities that, over the course of billions of years, would evolve into stars, galaxies, and eventually you sitting here, wearing your favorite pajamas, watching a video about the universe. Those minute differences are clues. They tell us how matter was spread out in the beginning of the universe. They reveal the physics of the cosmos at its birth, and they let us test theories about how space and time unfolded in the first few heartbeats of creation. Even the form the CMBB bears the imprints of a universe. If the shape of space were a sphere, saddle, or pancake-like flatness, those geometries would subtly distort the way light travels through space. By determining the magnitude and distribution of the changes in using the CMB, scientists can deduce the vast structure of space itself. And so far, everything points to a flat universe, at least within the bounds of what we can observe. It's similar to analyzing the pond's wave pattern to determine the shape of the shoreline. Information about the surroundings is carried by the way those ripples stretch and move. In a similar fashion, the CMBB transmits encoded messages regarding the shape, size, and elements that make up the universe. It's light as data, photons as historians, and imagining that glow, that gentle wash, has a deeply calming effect. Of ancient light, calm, and even rather than dazzling or fiery. Not one that you can see with your eyes, but one that's always present. After all of this, it still sounds like the universe's own lobby. Years. If you could tune in with the right kind of radio, you'd hear it everywhere. Not as a song, but as a faint static warmth, a constant low-level presence woven into the very fabric of space. It comes the closest the universe has to a picture of a baby, a moment in time when it was just a baby. Clarity. Additionally, it continues to whisper to us long after the stars were formed. Long after the formation of galaxies and the slow dance of Earth around them, the sunlight, that light has crossed over generations of stars, unimaginable distances, and arrived here in your lifetime, ready to tell its story. The CMBB is something solid in a universe full of mystery, something that can be measured, plotted, and comprehended. It reminds us that we don't need to pursue space's outer edges to learn about its origin. There are times when the answers are already all over us, patiently waiting in the light. Therefore, the next time you look up at the night sky, try to imagine it as something other than black and empty, but filled with an ancient light too faint to see. It has been on the move over a period of more than 13 billion years, expanding with each passing moment and carrying the quiet history of everything. It continues to do so even now in the stillness of space, persists in shining. Is there a true edge to the universe, a final frontier, a cosmic curtain, some ultimate boundary where space just stops? It's a query that keeps bubbling up, not just in science fiction, but in real scientific circles, whispered between chalkboards, telescopes, and despite the fact that most cosmology favors a flat universe, some speculative theories and thought experiments nudge open the door to stranger possibilities, places where, even if we cannot quite perceive or feel them, boundaries may still exist. Let's start with a gentle suggestion that our three-dimensional universe might be like a brain or surface floating in a higher dimensional space. This is one of the central ideas in brain cosmology, an offshoot of string theory. Our universe may appear to be a vast, three-dimensional membrane in this representation. For the brain, which exists within a bulk of higher dimensions, we are confined to this brain. Except for gravity, all known forces and particles are confined here, like a soap bubble full of bugs. Gravity, being a bit more adventurous, might leak into the surrounding dimensions, which is one reason some physicists think it seems so weak. Compared to the other forces, our universe may have a distinct advantage that transcends three dimensions, if this hypothesis is correct. Space, but we are unable to directly perceive the bulk in higher dimensions. You could picture a limit on the brain or boundary in the dimensions we don't experience. From our perspective, everything appears to be continuous and edge-free. But from the perspective of a hypothetical five-dimensional being with excellent vision, we might look like a disk of cosmic matter with boundaries at its rim. The thought of being watched by something with more power is a little unsettling. Dimensions than we can comprehend, but comforting, too. We be the strange mystery to them. Then there's the idea of cosmic domain walls, boundaries. between various parts of space where the physics might be a little bit different. These walls are predicted by some theories of how the early universe broke symmetry. Imagine that there was a phase in space. Change like water freezing into ice, but it didn't freeze the same way everywhere. Some regions froze with one set of rules while others chose a different path. The borders between these patches could form domain walls. Massive structures stretch across space, dividing one cosmic regime from another. The majority of models would have these walls quickly disappeared or diluted into irrelevance, but some speculative scenarios imagine they could still exist, lurking silently like sentinels in deep space. It might not be dramatic to pass through one, or it might be like entering a slightly different universe, a different chemistry version. It's possible that your atoms will behave slightly differently. Your tea might taste, for no apparent reason, it tastes a little more lemony. Speaking of passing into other realms, some philosophers have pondered the possibility that our entire universe is contained within a bubble. Not in a literal sense, but literally. A bubble of space that formed during a phase of cosmic inflation. Imagine the universe's early days, frothing with quantum fluctuations. In some regions, inflation stops and a bubble of space forms with its own properties, including the constants of nature, the strength of gravity, the number of spatial dimensions. Each bubble is a universe unto itself. This is sometimes called eternal inflation, and it leads naturally to the idea of a multiverse, a foam of bubbles, each with its own unique physics. In this perspective, our bubble borders on a kind of edge. Universe comes into contact with the inflationary background or where it might eventually meet another bubble. But this collisions would be extremely uncommon. If we are a bubble in a vast cosmic foam, our neighbors are too far apart to ever meet, and the boundary of our bubble would be more abstract than concrete. Still, there's a strange poetry in imagining the universe as part of a fizzing sea of other realities, each expanding into the empty like dish soap. There is also Gödel's universe, which rotates. Yes, that Gödel, the same person whose incompleteness theorems shook up mathematics. In 1949, he formulated a solution to Einstein's equations that explains how a universe revolves as a whole. Individual, not galaxies that are still spinning, but the whole fabric of space-time is slowly twisting in the shape of a huge cosmic spiral. Time and space are curved in this bizarre model in such a way that you could theoretically travel a specific route and arrive back at an earlier point in time, essentially a time loop. Although there are no boundaries in Gödel's universe, the lines between space and cause and effect are blurred. Effect, which is more perplexing, the capacity to build a wall at the end of the universe, or who were you before you were born? Now, before you book your round-trip ticket to yesterday, it was important to note that the observed universe does not match Gödel's rotating universe. Our universe isn't spinning in that global way, and the kind of time loops he imagined remain theoretical at best. But the model is valuable, not because it's physically realistic, but because it stretches our minds. It reminds us that equations, not our imaginations, determine the universe's rules. And, occasionally, those equations permit worlds stranger than fiction. Another crazy idea is that the universe may resemble a hologram. Not in the sense of flickering projections found in science fiction, but in a very precise method in math. Everything that happens in our three-dimensional world is holographic, according to the holographic principle. A distant two-dimensional boundary might encode space, similar to how a hologram stores an entire image on a level surface. In this instance, the actual boundary of our universe is not a wall or border, but rather a boundary where the fundamental information is stored. We're not talking about simulations or digital trickery, merely a different description of the same physics here. The concept comes from string theory and black hole thermodynamics, and it's still speculative, but tantalizing. The underlying message of all these theories is not that there will be a physical wall or a sign that reads, "Authorized personnel only," at the end of the universe. It's that Space might have boundaries and limits that don't look like they do to us. There may be edges in higher dimensions, or in the initial conditions of our universe, or in the information that underlies everything. They might not appear to be walls. They might appear as alterations in physics, curvature, or the rules themselves. It's entirely possible that we live in a universe with no edge at all. However, it could also be that we're encountering concepts that appear to be edges, or the limits of what we can know, of what our equations can describe, based on what we can see. Additionally, isn't that a kind of boundary as well? We are living in rooms on continents surrounded by air, gravity, and things that end is how creatures evolved. So, when we move, we bring those instincts with us into cosmology. Because everything else in life has edges, we look for them. But, as always, the universe is not obligated to meet our expectations. Maybe the cosmos loops quietly in on itself. Perhaps it extends in all directions indefinitely. It might perch delicately on the surface of a bubble with a higher dimension. Or just maybe it has a shape similar to something that curves, connects, and folds in ways our minds cannot even begin to comprehend, has never been considered before. And yet here we are floating in that mystery, wondering about boundaries. While a member of something that may lack any, there's something peaceful in that. Don't you think that could the universe be infinite, not just in size, but also impossible? That the inquiries themselves may stretch on forever? Just trying to comprehend this universe with its billions of galaxies is a significant challenge in and of itself. Swirling black holes, cosmic background radiation, and space that might curve or stretch forever. There are already a lot to ponder. However, cosmologists and physicists like to stir things up from time to time. The pot, and ask an even bigger question. What if this universe isn't the only one? Welcome to the multiverse hypothesis. It's one of the most fascinating, bizarre, and thoroughly ideas in modern physics. They're speculative. It suggests very simply that there might be more than one universe, perhaps many more, maybe even infinitely many. Universes with distinct physical laws, particles, and timescales. Universes where cats walk on ceilings, gravity moves in the opposite direction, and your the choices for school haircuts were much better. Before we go too far, let's make something clear. There is no direct evidence for the existence of other universes. None. They're not visible to us. Measure them, wave to them across a dimensional fence. The multiverse is not a conclusion, but rather a framework. A means of thinking that arises naturally from certain theories, but still lives firmly in the land of speculation. That said, the idea isn't as wild as it might sound. In point of fact, there are a few different versions of the multiverse hypothesis, each with its own flavor of cosmic imagination. The cosmic multiverse, or bubble universe model, is the first and most obvious. Inflation is the source of this idea. Theory, the rapid expansion that occurred just after the Big Bang. In this perspective, inflation did not happen uniformly. Instead, it might have formed a number of distinct bubbles, each forming its own universe, expanding and evolving independently. Each bubble might have its own laws of physics. Some could be too strange to support matter. Other people may have entirely different kinds of particles, forces, or even dimensions. We occur to live in a fortunate area where stars, planets, and long-winded late-night conversations thrive. Podcasts. Our universe is modeled after a single soap bubble suspended in a cosmic foam. It's possible that additional bubbles exist, drifting indefinitely apart from our own. You're not far from imagining a cosmic sink full of dish soap. Off. Then there is the interpretation of quantum mechanics that leads to the quantum multiverse, specifically the many worlds interpretation. This version says that every time a quantum event has multiple possible outcomes, all of them actually happen in separate branching universes. Thus, in one universe, you hit snooze this morning and stayed in bed. In another, you got up early and made pancakes. In yet another, you try to make pancakes, but accidentally discovered teleportation instead. an entirely new version of reality that is created by how every choice and chance plays out. This is not merely an experiment in thought. It is a serious interpretation of quantum mechanics that was created to prevent wave function collapse's awkwardness. But like the bubble universe idea, it's not something that can be tested or observed right now. We can't jump between these branches. Interdimensionality does not exist. Train station with a mustachioed conductor offering trips to the universe where you became a world-famous harmonica player. And yes, in at least one of those infinite branches, you probably have a mustache, even if you've never grown one. Statistically speaking, it's almost certain, somewhere out there, you might be giving a TED Talk about alternate facial hair, choices, and how they affect different timelines. There's also the mathematical multiverse proposed by cosmologist Max Tegmark. This is the idea that all structures that are mathematically consistent are real and exist in the real world. In other words, if it can be calculated, it exists somewhere. This encompasses not only other universes with diverse particles, but ones with entirely different logical rules. Universes where pi has a different value or time circulates in a spiral. It's a bold suggestion, almost mystical in scope and probably impossible to test. But it's compelling to think that math itself could be the fabric of existence, resulting in the creation of every possible form of reality, like an endless library of cosmic blueprints. These multiverse, though intriguing, ideas do attract criticism, which is understandable. One of the biggest issues is falsifiability. If other universes are forever inaccessible, how do we study them? How do we know they exist at all? Science works best when we can test predictions, measure results, and refine our models. When we're talking about realms that can't be reached by any signal, it's hard to apply the usual scientific tools. For some physicists, the multiverse as a warning sign, a symptom of theories stretching beyond their useful limits. Others argue that the multiverse helps explain why our universe has the properties it does. If there are countless universes, each with different constants and laws, it's not. It is surprising that we live in a place where life is possible. It's a cosmic version of survivorship bias. We exist because this is a location where living is possible. It's similar to using it in a casino to roll dice. There are infinitely many tables. The majority of tables don't produce anything interesting, but by pure chance, the dice land at one. Exactly right, that's the table we're sitting at. We weren't dishonest. We failed. Rigged the contest. It just so happened that we were in the room where the calculations were made. Some cosmological models even suggest that multiverses may be detectable indirectly, perhaps through unusual patterns in the cosmic microwave background caused by collisions between bubble universes. Nothing has emerged so far, but scientists are being open-minded. After all, some of science's most amazing discoveries began as strange concepts need the right tools. Thinking about other universes challenges us, regardless of whether they exist. Imaginations. It encourages us to think beyond the limits of what we can see. It reminds us that reality might be far broader, stranger, and more playful than we ever expected. It invites us to be humble in the face of what we don't know and bold in exploring what we might eventually learn. And isn't that, after all, what science is all about? Not only providing answers to inquiries, but also locating bigger ones. Not just building knowledge, but expanding wonder. Even if we never find another universe, even if this one is all there is, we've already proven that human curiosity can reach across galaxies through time and into ideas as vast as the multiverse itself. That's no small thing. So whether you believe in a single cosmos or an infinite stack of them, whether you prefer one timeline or a branching forest of quantum possibilities, remember somewhere in the multiverse, you're involving a llama in a brilliant, unusual, or inexplicable way. You're here in this universe, too, thinking about space, sipping tea, and quietly wondering what else might be out there just beyond the veil of what we know. That in itself is a kind of cosmic magic. Where does space stop? It's the question that brought us to this point, whispered at the outset like a child asking if the sky has a beginning or an end. And after, wandering through galaxies, curved dimensions, cosmic microwave whispers, and we find ourselves gently circling back around the possible edges that may or may not exist, to where we began, still wondering. We now know that space behaves differently, like a room, a box, or a road stretch. It doesn't come with a fence or a finish line. It doesn't need walls to be complete. It can be infinite or finite and unbounded. It is flexible, loopable, fold and curve in ways that our minds are only just beginning to comprehend. It can even move galaxies further away from us. Over light, the gap between us is widening, not because they are moving. We are aware that what we can see is limited, a cosmic horizon beyond which light has not yet reached us. But we don't know what lies beyond it. Maybe the universe keeps going forever. Or perhaps it wraps around itself in a gentle arc that we will never see. Perhaps there's just one bubble in our universe, many drifting in a higher dimensional sea. Alternately, the multiverse might just be a beautiful but unreachable poetic concept. Space is not. That much is certain. Empty. It's alive with structure and subtle energy. It stretches with time. It carries the light of ancient stars and the hum of the Big Bang. It has no center and, as far as we can tell, no end. There's still questions. Is the universe infinite or just very large? Is it curved, flat, or something else entirely? Is it the only one or one of many? Additionally, if space had a boundary, what would the other side contain? We won't ever have all the answers, but that doesn't mean we failed. It is the lifeblood of science. The beauty of the cosmos isn't just in what we know, it's in what we don't. It's in the quiet courage of asking while looking up. Regardless, the investigation continues as it always has. Through equations and telescopes, gentle dreams and late-night thoughts. Each and every photon that we detect, every map we create, and every model we refine brings us closer, even when the destination keeps shifting like the stars. Perhaps that is the entire point. Maybe space never stops. Not due to its size is infinite, but its mystery is infinite. Maybe it doesn't have to end in order for it to be important. Maybe it just is silently spreading out in all directions. An invitation, not a restriction. In the introduction, I asked a few things for you. What time it was where you were listening from, and whether the question, where does space go, stop, might keep you awake or lull you to sleep. I hope you're feeling better now. I hope your thoughts have softened into that quiet space where wonder lives. And even if you're barely awake, I hope you've found some peace in the act of asking, even if the response is still elusive. Because, in fact, that is what space provides for us. Not merely stars or silence, but the liberty to ask the most important questions. Additionally, due to questions, perhaps space never ends. Never do so.